Okay, so the next thing we're going to be talking about is chapter 5.7 over inverse trigonometric functions and how we are able to differentiate them. So looking at the differentiation of inverse trig functions. So the main things we'll be looking at today is looking at the developing the properties of the 6 inverse trig functions, being able to differentiate an inverse trig functions, and review some of the basic differentiation rules for other elementary functions that we did early on. So first off, the inverse trig functions. So remember that when we talk about the trig functions, sine, cosine, tangent, cotangent, cosecant, secant, that all of them were quote-unquote periodic functions. So technically, none of them are one-to-one, right? Because they all repeat. So if you ever recall looking at a lot of the graphs, you look at sine and cosine, they kind of look like they have graphs. They just kind of look like humps in a sense, or kind of like waves, sound waves, frequency waves, things like that. And then you have like cotangent and tangent, which look a tad bit different, but it's the fact that all of them repeat after a while, so they're not one-to-one. So now we examine whether, can we restructure the domain so that they are one-to-one. We can't talk about the inverse trig functions until we determine that they can have an inverse at first. So now we look at if we restrict each function, each of the trig functions to a certain domain, then we are able to have an inverse function. We're able to make them one-to-one, which gives them an inverse function. So if we look at this column right here, remember, the functions right here we're talking about, these are the actual inverse functions. So we have y equals arcsine of x, if and only if sine of y equals x, and then so on and so on for the rest of them. So this side, this says domain and range. These are the domains and ranges for the inverse trig functions. So when we're looking at the regular trig functions, remember, these flip. So this side right here consists of the domains for the regular trig function. So if we look at sine, for example, sine of y equals x, that means y has to be within this range in order to make it one-to-one. Within this domain to make it one-to-one. There's a bunch of different domains that you can use when restricting them. When restricting these trig functions, these are just more so the more so basic ones that we use. Kind of the parent domains, if you will. These are the domains that we usually go off of whenever you like go on your calculator and you take like arcsine and things like that. It always puts you in these intervals. So these are the intervals that we like to use. So as you can see, sine of y has the domain from minus pi over 2 to pi over 2. Cosine has from 0 to pi. Tangent has from minus pi over 2 to pi over 2, not including the endpoints. And then so on and so forth for the rest of them. So let's move on. So right here, you kind of see an example, just what the graphs of the 6 inverse trig functions look like. As you can see, based off the domains we give them, based off the domains they're given, because remember, their domains are the ranges of the regular trig functions, and so they should look familiar. But notice if you just look at all the graphs, they're all going to be one-to-one. Which is what you want. Your invert, when you talk about finding an inverse function, your inverse function should also be one-to-one. So the only ones that look kind of weird are these, but as you can see, this one has a horizontal asymptote at pi over 2, so you never have to worry about this part crossing over, this part crossing over, and so you never have to worry about this not being an inverse function. Same thing, this one has a cosecant, so arcsecant has a horizontal asymptote at pi over 2. Cosecant or cosecant inverse has a horizontal asymptote at 0, at y equals 0. So you never have to worry about these lines crossing over. Thus, you never have to worry about them being not one-to-one. So if we look at some example of just being able to evaluate inverse trig functions, remember the domains that you're in. So if we look at arcsine of minus 1/2, remember there's plenty of numbers that when you take sine, there's plenty of angles such that when you take sine of it, they can give you minus 1/2. However, we want to find one such that it's in this interval. So I want to find it such that it's minus pi over 2 less than or equal to y less than or equal to pi over 2. So it needs to be in that particular interval. So then if we're looking, there's only one angle that's going to be in that interval, and that angle is minus pi over 6. Okay, and you can find that from looking at your unit circle. Remember, sine is an odd function, so if you think about arcsine of 1/2, arcsine of 1/2 itself would just correspond to pi over 6. So then arcsine of minus 1/2 is going to correspond to minus pi over 6. Okay. So for B, we're taking arc cosine of 0. So then same idea. We want to look, remember, for numbers that are within this interval. There are infinitely many that give you 0, but we only want to look for one in that interval, and the one that we look at is going to be pi over 2. So again, another value you can also find from your unit circle. We have that, remember, y equals arc cosine of 0 implies that cosine of y is equal to 0. So in that particular interval, it's going to be at pi over 2. Okay, for C, so we're looking for arctan of square root of 3. So then we're looking for a y such that y is equal to square root of 3. We're looking in the domain of minus pi over 2 to pi over 2. And so we're given that y has to be pi over 3, or 60 degrees. And then sometimes you'll get random numbers like 0.3, which isn't quite on the, it's on the unit circle, but it's not typically labeled like the rest of them. So this is one of those ones you want to put in your calculator and usually set in radian mode. And you'll get, if you set it in radian mode, you'll get that it's approximately 0.305. Remember that inverse functions have the property such that when you take the composition in either order, you're going to get x back. So when you take the composition of a number, you should get that same number back no matter the order of the composition. So remember that when we were looking at these, when applying these to the inverse trig functions, that we had to restrict the trig functions to certain domains. If we don't keep them inside of these, if we don't stay inside of these restricted domains, then the properties will not always hold. So for example, a famous example is if you do arcsine of sine. If you were to take sine of pi, we know that sine of pi is going to be equal to 0. But then when we look at arcsine of 0, if you were to put that in your calculator, it's automatically going to put you in that minus pi over 2 to pi over 2 range. And so we know that arcsine of 0 in that particular interval is going to be equal to 0. So then we have a situation where we started out with pi, but then we got 0. We didn't get pi back. So you see, but it's because of the fact that we chose a number that wasn't in that restricted interval. So now we have just some different properties. So likewise, when we're back at this slide, when we have the domain and the range, so we have the domain of the arcsine was minus 1 to 1, and the range was minus pi over 2 to pi over 2. So then when we look at this particular property for arcsine and for sine and arcsine, we have that if as long as x is in between minus 1 to 1 and y is in between minus pi over 2 to pi over 2, then we have that the properties will always hold. If we get outside of these intervals, and more in particular, we can't get outside the interval for x because we can't anything outside the interval for x. This is just undefined. So we don't have to necessarily worry about that. But if we get out of this interval for this, we can get something that's defined. You just won't get y back. You can plug in anything you want here, but if you're outside of this interval, you won't get that same number back. So for the next one, if minus pi over 2 is less than y less than pi over 2, then we have the following properties for tan and its inverse function. So note that it doesn't have anything for x here, and remember for x can basically be any real number. Remember, if we look back at arctan, the domain of arctan was all real numbers. Because for x, when you're taking, because if you think about this part, if you think about tangent of y, any angle that you put in, you can literally get any number from putting in an angle, because of the fact that when you think about tangent as sine over cosine, your cosine, whatever you get for cosine, can be a number that's so small such that it makes that fraction, that whole fraction, the sine over cosine, it makes that fraction get really big. So your number can get really big, which is why it can be any real number. And likewise, it can get really small, or it can, still get really big, but going on the negative side. So then when we look at those properties that we were looking at, that's why it doesn't include the x part, because we know that x can be any real number. So it just sort of omitted that. But we do need y to be in the interval minus pi over 2 to pi over 2. It can't be either minus pi over 2 or pi over 2, because remember, tangent at minus pi over 2 is undefined because of the fact that cosine is 0 at this point. And the same thing, cosine is also 0 at this point. So tangent will be undefined. That's why we don't include the endpoints. And then for secant, we have that x has to be, secant and arcsecant, we have that x has to be either greater than 1 or less than minus 1. That's just what this inequality means. So that the absolute value has to be greater than or equal to 1. And then that y has to be either in between 0 and pi over 2, not including pi over 2, or it has to be in between pi over 2 to pi. So basically 0 has to be in between 0 to pi, but it can't be equal to pi over 2. And then we have that it holds as long as we stay within those intervals. So example 2, if we have, let's say we want to solve an equation, arctan of 2x minus 3 equals pi over 4. The first thing we want to do is notice we have an angle. We want to get rid of this arctan part. So to do that, we're just going to take the tangent of both sides. As long as we take the tangent of both sides, these will cancel out. And then we have tangent of pi over 4, which if you go back and look at your unit circle, that's just sine of pi over 4 and cosine of pi over 4, which those two things are actually equal. They're both like square root of 2 over 2. But if you divide one number by the same number, you're just going to get 1. So tangent of pi over 4 is just equal to 1. And then you're left with 2x minus 3. And so then what you want to do next is just algebra at this point. You add 3 to both sides. This 3's cancel out. This becomes 4. So you get 2x equals 4. And then you divide both sides by 2 to get rid of the 2. So then you have like x equals 4 over 2, which is just 2. So now that we've looked at the inverse functions, the inverse trig functions, and that we've defined certain properties for them, now we want to look at what the derivatives look like. And so just a quick note that if we look at f of x, ln x, we know that ln x is a transcendental function, whereas its derivative is an algebraic function, which essentially just means that we can find a polynomial such that when we plug in this function, we can get 0. Whereas it doesn't work. Whereas ln x, we can't do that for ln x. So that's essentially the main idea, the main difference between transcendental and algebraic. So now we're just going to see that. Notice that the inverse trig functions are transcendental. The inverse trig functions are transcendental. But you'll notice by the way that they're inverse, by the way that the derivatives look like, the derivative functions are actually going to be algebraic. So if we look at this chart, we can see the derivative, and some of them you can see they're sort of kind of related. So if you look at the derivative of sine of u, whereas u is just the inside function of sine, you get that it's u prime over 1 minus u squared. You get that the derivative of cosine inverse is essentially the same thing, but it's the negative version of that. So it's the same thing as the derivative of arcsine, but it's just with a negative sign. Arctangent is u prime over 1 plus u squared. And then cotangent inverse is the same thing, but also with a minus sign. And then you have arcsecant, which is u prime over absolute value of u times the square root of u squared minus 1. So you can see these sort of flip, and then this is added in there. And then our cosecant is the same thing, but it's the negative of it. Okay, so if we look at a few different examples, we have that arc sine of 2x. If we take the derivative of arc sine of 2x, our 2x is our inside function. So when we take the inverse of 2x, we just get that is 2. And then our original u is just 2x. So we have 2 over square root of 1 minus 2x squared. And then if you simplify that, you just get 2 over square root of 1 minus 4x squared. Likewise with our tangent, remember the derivative was u prime over 1 plus u squared. Our u in this case was 3x, so u prime is just going to be 3. And then we just square the u. So then once we square it, we square the 3 and the x, so we get 3 over 1 plus 9x squared. Then we look at arc sine, the derivative of arc sine of square root of x. Remember with the square root of x, that's the same thing as saying x to the 1/2 power. So when we take that derivative of the inside function, we get that it's 1/2 times x to the minus 1/2. And then this part is just square root of 1 minus x. Because remember the x to the 1/2, when you square it, it just becomes x. And then when you simplify this, remember it's a negative exponent, so you can just bring that on the bottom. That's where the square root of x come from, and this is 1/2, so you leave the 1 up here and bring the 2 down. And then you can put these roots together by since they're both square roots, you just multiply the inside parts. So it's x times 1 and then x times minus x squared. So then you got x minus x squared. So now we look at the derivative of arc secant of e to the 2x, where it was just, we take the derivative of the inside function, which is just 2e to the 2x. Notice we were going to put the derivative, remember the inside, remember on our derivative formula that it's the absolute value of u. However, note that e to the 2x is always positive, so for that reason we don't have to put an absolute value on that one. And then we just plug in our u, so e to the 2x we square it, which is just e to the 4x. The 4x, notice that we have e to the 2x right here, e to the 2x on the bottom, that's being multiplied, so these can actually cancel out. And so we're left with 2 over square root of e to the 4x minus 1. And then, just as I stated before, the absolute value sign wasn't necessary because of the fact that e to the 2x is always greater than 0. So now we're just going to simply just review some of the basic differentiation rules. So if we look at, just remember an elementary function is just a function from the following list, or one that can be formed as a sum, product, quotient, or a composition of the functions in the list. So elementary function, we just mean polynomial functions, rational functions, functions involving radicals, and then of course we have our elementary functions for logarithm, exponential, trigonometric, and so when we look back at some of the differentiation rules, these are just all the rules that are listed out. So you have your, product rule, your addition and subtraction, quotient rule, the rule for constants, the rule just for x itself, which kind of goes with the power rule. This is sort of the power rule combined with the chain rule, and you see a lot of these after you get to a point. A lot of them are combined with the chain rule. You have the derivative of absolute value, derivative of ln of u, the exponential function, and then we get into a little bit more complex ones with the logarithms, more exponential, but instead with a base different other than e. Notice that the difference between this one is this one has the ln a up there, whereas if we include this one with ln e, just note that ln e is just equal to 1 because ln of e is already has a base of assumed e. So ln of e is just 1 itself, so it's just 1 times that. So that's why that's not written there. It's pretty much silently implied. And then you have, of course, your derivative of your trig functions, and then it goes your derivatives of the inverse functions. And that is it. So for the next section, we looked at this section, the differentiation of these inverse trig functions. The next section will be over the integration of the trig function.